Hi, I'm Josh Borrow from the Institute for Computational Cosmology at Durham University. Today I'm going to be talking about smoothing SPH data to fixed grids in an adaptive context. Here by adaptive, I'm referring to our specific use case, which is galaxy formation simulations. In these simulations, there can be a 4 order of magnitude difference between smoothing lengths. And so it can be challenging not only to run them, but to post-process them. To meet in the middle with our observational colleagues, what we need to do is smooth the data that we have down to fixed pixel grids. So what we're doing there is effectively taking mock observations of fake galaxies. When you have a telescope with a camera attached, the data that you get out the other side is essentially just a pixel grid, it's an image, and we need to make that as well. Now, the key here is that these images aren't just for visualization. The specific physical quantities that we compare need to be accurately modeled. And the final caveat is that this also means that we can't just go to arbitrarily high resolution so that we know that every single kernel is well sampled by the pixel grid. We have specific dimensions, specific number of pixels that we need to target. What do I mean by projecting a particle or set of particles to a grid? Well, first let's get a grid, and then what we'll do is we'll take this black particle with its kernel extent shown by the dashed line, and we'll find all the pixels that it covers, those are the little crosses, and we'll evaluate the kernel at those pixel centers. What we've done here is a basic first order integration of the kernel over the grid, and this is typically what people use for this purpose. If we look at a slightly more complicated case, here we have a linear gradient in density, and what we'll do is we'll set up the particles, and then we'll take a look at individual particles, just showing you again the individual kernel smooth to the grid, and then we'll fill in the rest of the grid. So what you see here is the individual contribution of each particle to that smooth background gradient. The tricky part here is getting the same answer out no matter what resolution you use. Now, obviously, you're not going to get the exact same answer, but what you want to get at low resolutions of your grid is the same answer as if you'd taken a very high resolution grid and downsampled it to that resolution. What we'll do here is we'll go from the initial resolution down to an 8x8 pixel grid. And what you'll notice when we get down to these very low resolutions is that when particles start approaching the same size as the background grid, odd things can occur. So in particular, notice the bottom left particle and how its overlaps with all of the neighboring pixel cells aren't well calculated. All of its contribution has been given to one pixel. And that's because this particle only overlaps with one pixel center, even though it does overlap with multiple pixels. To look at this more numerically, let's take a look at how the percentage error on average, that's the circles, and the error bars show the 10 to 90 percentiles, changes as a function of grid resolution. You'll notice that this basic first order method does indeed converge as expected, but here there's no excuse in a static problem to get a poor result at low resolutions. What we need is a method that at these low resolutions is able to provide us with a well-sampled grid. Now, you may say, well, just take the high resolution grid that you have at the maximum where every kernel is well sampled and then downsample it to the exact resolution that you need. That's not always possible in a highly adaptive environment. To well sample every kernel, you may need a massive image, something like 128,000 by 128,000 pixels or 256,000 by 256,000 pixels. And those are just going to take a very long time to make, one, and two, trying to deal with images of that size becomes a big issue. If we look at this in a more astrophysical context, here is an image of the density structure in an isolated galaxy disk. This galaxy looks quite similar to our own, the Milky Way, and what you'll see is that there's a range of densities that span about 3 orders of magnitude. This is on the bottom of our adaptivity scale. When we start bringing in things like the gas that lives around galaxies and the gas between galaxies, that's when problems really start to grow. And what we'll see here is if we look at the specific places where the errors start to creep in this exact case, we see that it's the higher density regions, the kind of arms of the galaxy that we call spiral arms. And that's quite worrying. In SPH, and in adaptive SPH in particular, you would imagine that the most accurate regions are the ones that are highest density. In a finite mass method, what you want is as many resolution elements as possible, and so what you're doing there is resolving better and better, and hence improving accuracy. Here we see that the highest density regions are actually the least accurate. And that's quite a worrying error structure to play with. It's completely against our natural intuition. Looking at this numerically, we see that the errors do again converge well, but we see a significantly larger span in the percentile range of errors. In some cases, individual pixels are very well characterized at any density, and that's because those have very large kernels in them. And then there are some pixels which struggle to get under the even 1% error margin, even at high resolutions. This really motivates the need for a much better method. So how do we improve, and how do we get a better reconstruction at all resolutions? Well, the approach that we've taken to fix this is by subsampling the grid. So for particles that are very small kernels, what we do is we use a pre-calculated 32 by 32 pixel grid that displays one kernel, and we overlap that with the background pixel grid. We then use this to appropriately weight the pixels over which this one kernel overlaps. For particles that overlap multiple pixels, but not very many, what we can do is we can ensure that every single particle is resolved by at least 32 by 32 kernel calls. We do this by, for each particle, generating a subsampled grid and then evaluating the kernel across this subsampled grid. Another approach here would be to use a higher order integration method for each pixel, but typically using these higher order methods is slower than just using more kernel calls and using more resolution elements in a lower order method like the one that we use here. With these combined, we can go back to the gradient exercise and see that we produce converged results at every single resolution level. Everything here is below 0.1% error. We can reduce this further by either using those higher order methods or increasing the number of kernel calls that we use in each subsampled case. For us, a 0.1% error is probably good enough. For the astrophysical case, the same story is true. Here, the subsampled method manages to reduce the errors significantly across the board and produces converged results, even from the lowest grid resolutions. Finally, we'll look at the runtime cost of this method. Compared to the original method, which we show here in blue, we see that the new method is more expensive, especially at low grid resolutions. Here we're showing the cost per pixel. Now, compared to running a very large grid and downsampling that, that's the red lines, we do much better. It's over an order of magnitude faster. And this is the only real competition to using something like this subsampled scheme. So using the subsampled scheme not only gives you much more accurate results, it does so at quite a relatively low additional cost in runtime and significantly lower than what you would need if you were going to use a fully sampled method. Thank you very much for listening. If you have any questions, please feel free to contact me, and there's significantly more information available in the paper, and I encourage you to read it if you get the chance.